So water is amphoteric, meaning it can act as an acid or a base. Auto-ionization, as the name suggests, is something ionizing with itself. So it's a process by which water acts as an acid and as a base with itself. So we have seen examples where water acts as an acid. Here it's the proton donor giving a proton to ammonia. Here, water is acting as the base. It's accepting a proton from this acid. But you can also have an acid-base reaction between two water molecules where one acts as the acid and one acts as the base, and you get hydronium and hydroxide ion. Now, do you think this would happen a lot? No. I mean, because why? Why would it do that, right? Most things we see are going towards everything being the same. Why would we have two molecules that are the same spontaneously become different? Right? This is an equilibrium and has a very small equilibrium constant, but it does happen. This is called the autoionization of water.
Can you make that happen experimentally?
Well, it's always there in water.
Doesn't it happen like instantaneously because it's going back and forth?
Yeah, it is going back and forth. This is a dynamic equilibrium, and so it's not that one water molecule passed off its hydrogen ion and then they're always like that. It's that this one's being tossed around and it's just being traded off, right? So we can look at this autoionization. We can say that H2O forms H plus and OH minus. And here what we're doing is we've just taken a water molecule out of there, so we're not looking at hydronium anymore. We're just looking at hydrogen ion. But the equilibrium constant for that, water is a liquid, and liquids and solids, their concentrations don't change, and so they don't show up in equilibrium constants. So the equilibrium constant expression here is hydronium ion times hydroxide ion, or hydrogen ion times hydroxide ion, same thing, and that's Kw. And Kw is called the ion product constant for water. It's water forming ions with itself. At 25 degrees Celsius, Kw equals 1 times 10 to the minus 14. So that's pretty small. This is a number that you should remember. That one right there. 1 times 10 to the minus 14. So in pure water, if you start with all H2O, and then this happens a little bit, the hydrogen ion concentration and the hydroxide ion concentration have to be equal, right? Because they were originally together and they separated. So the hydroxide or hydronium ion concentration and hydroxide ion are equal in concentration, and you can solve this and find out that that's the square root of Kw, which is 1 times 10 to the minus 7. So 1 times 10 to the minus 7 is the concentration in moles per liter of hydroxide ion and of hydronium ion in pure water. Pure water is said to be neutral because the concentrations of hydronium and hydroxide are equal to each other. It's not that there isn't any hydronium ion, that there isn't any hydroxide ion, but they are equal to each other. In an acidic solution, we have an acid, and the presence of the acid creates extra hydronium ions. But this ion product constant for water still applies. So what happens is, because of the addition of hydronium ions, the equilibrium will shift. The hydroxide ion concentration will decrease, and we'll end up with the hydronium ion concentration greater than the hydroxide ion concentration. In a basic solution, we're adding hydroxide ions. That causes the autoionization equilibrium to shift, decreasing the hydronium ion concentrations, and we have hydroxide greater than hydronium ion. It is so cool. He's making connections. So the hydronium ion concentrations of 3 solutions at room temperature are as follows. Which solution is acidic? So we don't need to do a calculation here. What is the hydronium ion concentration of pure water? 1 times 10 to the minus 7. And an acidic solution is going to have more acid, right? So we're looking for the one who has a hydronium ion concentration higher than 10 to the minus 7. Now this is where negatives can just really mess with you, because something raised to the negative 7 is bigger than something raised to the negative 9, right? And so 10 to the minus 3, this is actually the highest concentration. And you can write that out in decimal form if you get confused. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9.
Is it okay to just like, for when it's concentration of hydronium ions, you can say that its pH is just the negative exponent, and then if it's OH.
We'll get to that. Just hold on just a minute. Yeah, it is definitely related to that. So that's the one that's acidic. So this is acidic because the concentration of hydronium ions is higher than in pure water. Acid has been added. So if we think about this in terms of an equilibrium, so we have our equilibrium expression here, right? It auto-ionizes and forms hydrogen ions and hydroxide ions. If we add some hydrogen ions to the solution from an acid, that's going to cause the equilibrium to shift to the left. It will reduce the hydroxide ion concentration. It will somewhat reduce the hydrogen ion concentration from what the maximum when it was added, but it can't bring it all the way back down. And the product of these is still going to be 10 to the minus 14. If we add hydroxide to the solution, it will also cause the equilibrium to shift, reducing the hydrogen ion concentration, so the product of these two is still 10 to the minus 14. But in that case, the hydroxide ion concentration is greater. So an acidic solution has higher acid, H+, and a basic solution has higher hydroxide. Calculate hydronium ion concentration at 25 degrees C for each solution and determine if the solution is acidic, basic, or neutral. Well, what's the equation that we need? We need the equilibrium constant for that equation. Kw. Kw is H3O plus times OH minus. And at 25 degrees Celsius, that is equal to 1.0 times 10 to the minus 14. So we're given the hydroxide ion concentration, asked for the hydronium ion concentration. So we can take this equation and solve it for hydroxide ion. Hydroxide ion concentration equals 1.0 times 10 to the minus 14. Wait, solving for the wrong thing. I'm solving for hydronium ion. Okay, calculating hydronium ion concentration from pH. Let's just make it, I didn't skip anything. Well, we know that pH, well, yeah, you gotta actually use, can't write with nothing, I have to pick a pen. Okay, pH is equal to negative times the log of hydronium ion concentration. But we want hydronium ion concentration. So if I multiply by -1, now I have negative pH equals the log of the hydronium ion concentration. And what's the opposite function of logarithm? 10 to the x. E is natural log. So this, I'm gonna take the anti-log of both sides, and I'm gonna end up with T for 10. 10 to the negative pH is equal to the hydronium ion concentration. So the hydronium ion concentration is equal to 10 to the negative 8.37. Now, that's a perfectly fine number, but we don't use numbers like that, right? We like our exponents to be whole numbers. So we need to do this on our calculators and get an actual number. So I'm going to press my 10 to the x button. So on my calculator, there's an E and 10 on the same, and if I press the button twice, I get 10 to the, and then I put in minus 8.37 and press enter. And my calculator is showing me this. Let's see. 1, 2, 3, 4, 5, 6.
To the 9th, right? -9.
1, 2, 3, 4, 5, 6, 7, 8. Now, is that actually 4, or is it maybe 3.8 or something rounded up? How would we tell? Yeah, so this is 4.26. So I need to tell my calculator to show me this in scientific notation instead. It's showing me in decimal because it can. It can get one digit and show me in decimal, but it's not very helpful. So I'm going to press mode and go down to the norm, sci, engineering, press sci, press quit, and then I'm disturbed because my number's gone. And so if you press equals again, it'll come back to you. And so this is 4.2657959 times 10 to the minus 9. How many sig figs should that have? 2. Because this is a pH, and the 8 is a placeholder, and the 3.7 is, so 4.3 times 10 to the minus 9. Because when we go the other way, only the digits after the decimal point come from this part. The 8 comes from this. Question?
It was like 8.3 or like 8.1234, so we would have like 4.
Yeah, if it was like 8 point, let's call it 8.3700. We'd have to show 4, and we'd have to go out to here.
But so say leading zeros, because these zeros don't count, so oh, but never mind. I'm thinking
Yeah.
too much.
Yeah, you are thinking too much. Because in the pH, we're not going to end up with leading zeros. Any other questions? We're just going to finish this whole pH business and then stop for the night.
How many sig figs did you use again?
2.
2.
Mm-hmm.
Because, what if I again? Heard everyone react.
I used 2. Whoops, now I've lost it. Come back to me. It gets so lost in here. Because in 8.37, so this is the negative log of a concentration. And all the digits to the left of the decimal point are placeholders. And only the digits to the right are significant digits.
Oh, so you did 4.27.
Yeah, it comes from this. In a logarithm, only the numbers to the right of the decimal point are sig figs. So we just talked about pH. We can also talk about pOH. And that's just the negative log of the hydroxide ion concentration. So P is a mathematical operator. It's a mathematical function. It's negative log. And so we can have pKa. We'll be doing that. That's just the negative log of the Ka value. We can have P of anything. We can look at the pK. Well, that's a bad example. That would be potassium. But the pCa, the calcium ion concentration, we can express that as the negative log of the calcium ion concentration. So P just means negative log of. And so we see here for the pOH concentration, pOH values, those also range from 14 to 0, but they are opposite of the pH. One goes up when the other goes down, because the product of hydronium and hydroxide ion concentration is always 10 to the minus 14. Derive the relationship between pH and pOH. Well, pH is the negative log of the hydronium ion concentration. And pOH is the negative log of the hydroxide ion concentration. Right? Well, what do we know about the relationship between H3O plus and OH minus? Their product is 10 to the minus 14. Right? So I'm going to take the negative log of both sides of this equation. So I'm going to get the negative log of H3O plus times OH minus is equal to the negative log of 1.0 times 10 to the minus 14. What is the negative log of 1.0 times 10 to the minus 14? It's 14. When I take a logarithm of two numbers that are multiplied, I'm adding the logarithm of each of them. So this is the same as negative log of hydronium ion concentration plus negative log of hydroxide ion concentration. The log of A times B is equal to the log of A plus the log of B. Well, what is that equal to? Negative log of hydronium ion concentration. Just pH. So we got negative log of hydronium ion concentration up there. So that's pH. Whoops. pH. And negative log of hydroxide ion concentration is pOH plus pOH equals 14. So this can be a simpler way to get between hydroxide and hydronium ion. Yes?
Do you have room to do this?
I will never make you derive this for me, no. I just, at this, so we talk about these equations in Chem 3A, but we don't really expect them to understand logarithms. We have just been through a horrendous chapter with logarithms in it, and so now we should have some grasp of logarithms. So now you're capable of understanding how this works. And so when you see how it comes together, it's like, wow, that's really cool. You don't have to remember how to do this, but you should remember how to use the equation. Understanding why is really helpful, yeah. So that brings us to the circle of life, or pH. I need a soundtrack here. Yeah. Because I'm trying to be funny. It's a joke. Haha, it was so funny, right?
LOL. LMAO. ROFL. What's the other one?
Oops, that's not being very symmetrical. That's kind of a circle. It could be a square, but circle of pH sounds better than the square of pH. So this is the circle of pH. You can convert between H3O plus and pH. You can convert between pH and POH. You can convert between POH and hydroxide ion concentration, or between these two. Is it possible to go straight across? Well, sure, you could derive an equation for that, but why? Why climb over the mountain in the middle? Just take 2 steps and go around the side. If you're here and you need to go there, don't go around the long way. I mean, it works, but why? So here are the relationships between these guys. So pH is negative log of H3O plus, and H3O plus is 10 to the negative pH.
You should trademark that.
I'm sure somebody else has done it.
That's okay.
So we should remember these equations. And the equations up here are the same ones that we use down here. We're just going to put in OH instead of H3O plus. So POH is equal to the negative log of the hydroxide ion concentration. Hydroxide ion concentration equals 10 to the negative POH. The one on the bottom right here is my favorite because it's easy. That's the one we just derived. And you can think of that 14 as an exact number. And then in the upper left, that's the one we looked at first. That's the KW, ion product constant for water. So those are some useful relationships. Any questions? I'm just going to take a screenshot of this and save you guys the trouble. So as the pH of a solution increases, gets higher, what happens to the acidity of the solution?
It's lower.
It gets lower. The acidity decreases as the pH gets higher.